pull that over and it'll get darker green. So now you're online.
Cool.
Hi, everyone. So for those watching online, I know you thought that Wednesday's session was the last episode, but turns out that the season finale of CS229 is today. Okay, so welcome to this session, and today, Xiaoyan, Zara, and I are going to tell you everything you need to know about convolutional neural nets. And more precisely, we're trying to give you a good high-level intuition on how these neural networks work and how they can help you in practice. And in order to do so, we're going to adopt a top-down approach where I will first deal with high-level details about these conv nets, and more particularly, how they evolved along the years and what kinds of tricks helped us make them work well. In the second part, Zara will talk about a bit more about the specifics of how these kind of networks work, in particular talking about kinds of parameters that are in there, how they match together, what's going on behind the scenes. And then last but not least, Xiaoyan will talk about the thing you may be the most excited about, which are the applications of these conv nets, so how you can apply them in practice, and what kinds of problems they can help you solve. But first, we noticed that recent research in deep learning has been largely inspired by the way our brain works. And when you think of it, it's fascinating to know that with a given input, our brain processes features that helps us solve supervised tasks like image recognition. Therefore, the study of architecture is crucial for us, not only because it helps us solve these tasks that we are interested in, but more interestingly, the architectures themselves point us out to the representation that researchers were looking for in order to better learn from the data. But first, before talking about conv nets, let me briefly come back to one point that we had in lecture. So in lecture, we talked about classifying an image, okay, with an output, let's say, binary 0 or 1. And at some point, one approach we proposed was from the raw pixel input, flatten this as a flat vector of pixels, and then plug in some neurons on top of them, and then add some layers directly acting on the raw pixels. Now, I have a question for you all. Who is happy with this kind of representation? Yeah, exactly. No one. So you can see that we have three main problems here. First, here we have a small image, okay, 64 by 64, three channels for the colors. So you have maybe like 1,000 features. And if you connect each of those 1,000 features with each neuron of your first layer, then you realize that that's a lot of edges, and hence a lot of weights. And you can see that if you operate on such big input, your calculations can quickly become intractable if you add more layers on top of them. So that's the first issue, but that's not the biggest one. Second one, as you can see, these pixels are highly spatially correlated. So for instance, let's say I translate a little bit this image to the right, okay? And let's look at the flattened input. These pixels will change drastically in position, whereas the meaning of the image is more or less unchanged. So we need something that conserves the meaning of the input with respect to spatial transformations. So that's the second concern. And then, so this points us out that we need first to extract low-dimensional and meaningful features out of our inputs. And in order to tackle this issue, the pioneer of ConvNets, Yann Lequin, proposed some kind of architectures 20 years ago, which is this pioneering architecture, which consists of inputting an image, okay, and you have a first layer of convolutional filters that will scan the image, and that will, for each convolution, produce one pixel of the output, okay? So as you go and scan the image with the convolutional filter, you build what we call an activation map, which is the result of this convolution with respect to the input. Okay, so you do it a first time, and then a second time, and so on. And then this architecture also consists of pooling operations, which basically downsamples these features. And then, as this goes through these convolutions, we also have activation functions that aim at introducing nonlinearities in the network. And at the very end, the last activation map we obtain is then flattened and fed to what we call fully connected layers, which are basically the multi-layer perceptron we know. So we connect each of those pixels to neurons so that it can give us the desired output. Okay? And here, as you can see, this network is very handy because it's well interpretable. So for example, let's say here I have an image of a horse as an input. Then the first convolutional filters will detect low-level features like shapes, okay, for example, straight lines. And then as you go deeper, more and more subtle features tend to be captured by the network, such as eyes and ears. And so it's a very top-down architecture that reduces the dimensionality of your features and extract them on the fly. So that during training, all of these properties come from backpropagation when the weights are learned by the network. Okay, so these convnets appeared as a way to construct features that we would have had to handcraft ourselves otherwise. But then you might tell me, why were convnets not popular back then? And then I would say, well, we had not leveraged the full potential of them. And convnets came back to force a few years ago in 2012 with this pioneering architecture called AlexNet. So this architecture takes back all the main points of the LeanNet architecture, but adds 3 main new tricks that makes it all work a lot better. So first, he used one trick. It's about nonlinearities. So previously, the LeanNet architecture used the tanh function, okay, which has this formula, exponential and more importantly, this activation function has this shape. So towards minus infinity, it goes stable, and then it goes to 0, and it goes again stable towards plus infinity, such that the gradient in that region and in the region on the right tends to 0. Okay, and that's revealed to be a real problem for gradient propagation. So instead of that, AlexNet used another type of nonlinearity called ReLU, which you already know by now, which is basically defined as being the maximum of 0 and x. Okay, so basically it's 0 for negative numbers. And then for positive numbers, you always have a derivative of 1. So this revealed to be helpful for gradient propagation. So that was the first improvement brought by AlexNet. The second one was to introduce better regularization. So as you know, I've talked about these fully connected layers at the end. So for example, when you learn your features, you have your high-dimensional activation maps that are in the form of a volume that are then flattened, okay? And then when they are flattened, they are fed to a series of layers composed of neurons, okay? And dropout, what it does is that with the probability of p, at each forward pass, it forgets about some of these neurons. Okay, so let's say I do a forward pass, and for some of these passes, let's say this neuron and this neuron gets forgotten by the network. So as a result, it forces the network to learn with just a subset of the neurons, which proved to be very helpful for the network to focus more on the features rather than the images themselves. So just to give a concrete example of what dropout means, so today we are holding this discussion, and it's very likely then you'll have, after that, forgotten some parts of it. And yet, this is okay, because you will have only kept in mind what was essential. Well, hopefully. So the same happens for neural nets, and it enables them to capture better representation. So that's the second trick. And then the third trick has been focusing on data augmentation. So for example, in previous architectures, we had a set of training examples that we fed to the network. And let's say, for example, we have an image of a person that I feed to my network, and I want to identify him, okay? So previously, we just went over the samples and just fed these images without doing anything about them, okay? So AlexNet, what it did is that they used a technique to augment these data sets, and then by performing a series of transformations on the inputs, such that, for example, you don't get to input only the original image, but also variations of this image. So for example, if for our person we draw features that make it non-symmetric, let's say we have a nice haircut, okay? So for example, AlexNet said, okay, let's, for example, rotate our input sample, and the meaning stays conserved, okay? So we use this training image, and we also use a series of modified images that conserve the same meaning. So for example, rotation. Here we have flip with respect to an axis, okay? So let's say we flip this image that way. And other types of data augmentation also consist of translation. And, for example, crop. You crop and focus on one part of the image more precisely. So as you can see, for us, these new training samples have the same meaning, but for the network, it's as if it were new training samples. And once again, so this is called regularization because it helps the network to focus more on the features that make a sample belong to a certain class than the images themselves. Okay, so that was the third trick. And then as you can see, AlexNet was then much deeper in depth than LeNet. So that was the fourth trick, in fact. And when we look at the history of image classification, for example, with ConvNet, we can see that following architectures went on with that trend of going deeper. So for example, here, 2 years afterwards, this is VGGNet. And as you can see, it's much deeper in depth. And there is something else that's very special about this network. So can you see? Here, underlined in red, you can see that all these convolutional layers are 3x3 filters. Whereas before, we had filters of different length, of different size. So the thing is that using these small filters helps us a lot for different reasons. First, using a lot of small filters instead of bigger ones introduces more nonlinearity because after each convolution operation, as I said, we go through an activation function. Okay, so first, it introduces more nonlinearity into the network, which is good. And then, when we look at those filters, we can see that, in fact, stacking small filters together can be equivalent to using a bigger filter. And I'm going to show it to you right now. So for example, let's say that I'm stacking together two 3x3 convolutional filters. So let's say here, this is my input, okay? And let's say I'm first convolving this input with this 3x3 filter. So the result of the convolution of this input filter of this filter on the input will give me an activation map. And then stacking another filter on top of it means that I will convolve with a new 3x3 filter on this activation map to then produce a new activation map. Now, when I say that stacking two small convolutional layers on top of each other is equivalent to a bigger one, we're going to see what it means right now. So here, let's look at 1 pixel of the output, okay, just here. And let's see how we can produce it. So we know, with the rule of convnets and convolutions, that this first output pixel is the result of the convolution of this filter, okay, on the region of the same size of this first activation map, okay? And then when we look at this activation map, we can see, for example, that the first pixel, top left of this activation map, is produced the same way. It's produced by the convolution of this filter on the same portion of the region of the input. But then as you see how these other pixels are created, they are the results of the convolution of this filter on translated portions of the input. So for example, we see that the first output pixel is created by the convolution of this filter on this first region. Then the second one is translated by a stride of one, the third one as well. Okay, so now I have my 3 first output pixel here. And in the same way, I can see the total region covered by these convolutions is of size 5 by 5. So that way, we can say that stacking 2 convolutional filters of size 3 by 3 is kind of equivalent with respect to the output. It's equivalent to looking at a region of 5 by 5 of the input, which is the same as a 5 by 5 convolutional filter. So this, what I talked about, is called the receptive field size of this output pixel. And if you know the filter size of each layer, okay, and the corresponding stride, okay, so the stride is the distance you go at each convolution, okay, so for example, if you have a stride of 1, then all convolutions go one after the other just by translating with a distance of 1, each of your convolutions. And the formula to obtain the receptive field at a filter K has in fact a nice form in terms of the filter sizes and the strides given by this nice formula, which you might find helpful. With the convention that S0, the stride of layer 0, is 1. Okay, so for example, here we have F1 and F2 that are equal to 3, S1, S2 equal to 1. So you can see that R2, the receptive field size of the after layer 2, is equal to 1 plus 3 minus 1 times 1, which is 2, plus 2 again, which is indeed 5. Okay, so stacking small filters together leads us to an equivalent receptive field size as bigger filters. So that's the second good point, okay? But that is not it. There is another benefit of using small filter sizes, which is something that we care about a lot in practice, which is the number of parameters. Okay, we have less parameters to train in our network, which leads to less computations, and I'm going to prove it right now. So let's say instead of these 2 by 2, like 2 3 by 3 filters, let's say I had used 1 5 by 5. Then the ratio of the number of parameters between those two cases is, so in the case of a 5 by 5 filter, so I simply have 1 weight per slot. So and without counting for the biases, I have 5 times weights, okay? And in the case of 3 by 3 filters, I simply have 2, okay, because I have 2 of them, 3 by 3 weights, which is approximately equal to 1.4. So basically by using 2 3 by 3 filters, we have 1.4 times less parameters than with the 5 by 5 filters, which is good. And this is exactly the trick that VGG used. Okay, and just to give some order of magnitude, so all of these architectures are tested against some common benchmark called ImageNet, which basically consists of 1,000 classes of images containing in total 1 million samples. And comparing the error rates with those architectures helps us track the benefits of each architecture with respect to the other. So for example, AlexNet did about 15%. This is 7%. Okay. And the next architecture I'm going to present is called GoogleNet. So as you see, it looks a bit more convoluted, and this architecture bases its success on these modules called inception modules. So as you can see, at each step, we have layers of different sizes that go over the inputs and that produce different kinds of activation map. And then at the end of each of these modules, the activation map are concatenated together. So you might find this idea to be a little bit funny because it's not, like, it might not sound natural, but in fact it helps a lot in diversifying the features at each step of the network. And also, so based on this, you might say, well, Shervin, this is nice, but isn't that insanely expensive to compute? And then I would say, yeah, you're right. But the thing is, GoogleNet used a nice trick to counter that. And it used one-by-one convolutions. So one-by-one convolution, they just consist in reducing the dimensionality of the filters, of the depth, like the depth dimension, which in fact makes it so that all those operations are not so expensive. Okay, so it used the trick of one-by-one convolutions. So not only this reduces the dimension of your features at each module, but they are also beneficial from a representation perspective. And then you might ask me, why are these called inception? Well, the answer is you can see each of these modules as being some kind of small network, okay? And we have stacked these modules one on top of the other, so you can see this network as being a network of networks, where, like, hence the word inception, okay? And just for information, it produced an error rate slightly less than VGG, which was 6.7%, so it's good to know. But then people realized, so another thing that you might have seen on this architecture is that it's even deeper than the previous one, okay? Then you might say, well, it's super easy. Let's just build an architecture that's even deeper than before, and it will work for sure. Well, it turns out that's not the case. Do you have an idea of why that might not be the case? In one word, the gradient, ladies and gentlemen. So the gradient basically controls the flow of the updates of your weights. And for networks that tend to be very deep, we have the problem of vanishing gradients that occur. And in order to illustrate that fact, I am going to bring one of your best friends to the board. Yeah, so you're wondering who your best friend is? It's the chain rule. So let's look at previous situations, okay, when you stack layers on top of the others. So for example, here you have at some point an input x0. Okay, you have the first layer, then the second layer, and so on. And then at some point, at the very end, you have to compute the loss, okay? And let's call the intermediary results x1, x2, and so on. So here, let's apply your favorite tool on this architecture to see how we can update these weights. So here, if we apply the chain rule, you will see a formula that looks like this. Okay, so partial derivative of L with respect to the last element here, which let's call it xn, okay, times partial derivative of xn times partial derivative of x over partial derivative of xn minus 1, and so on until partial derivative of x1 over x0. So as you can see, this might be a little problematic because when the network tends to converge, okay, the updates in each of those layers will tend to be smaller and smaller, such that when you want to compute the gradient with respect to a weight that's far in the network, numerically, you will compute the product of very small numbers together. So for example, let's say you have a very small number here times a very small number here, and so on. You might end up numerically with a value of 0, okay, so no update at all. So these networks prove to be hard to train. And in order to counter that fact, ResNet imagines something else that's very, very interesting. It's the concept of the skip connections. So at each block, not only do the input feature go through layers, but they also get added through a skip connection, which is an element-wise operation. And this is really good because it creates multiple paths for the gradient to flow. And just to give an illustration of what one of these paths might look like, so for example, in the case of ResNet, you might have, okay, maybe one module that operates on the input, and then based on all these skip connections, you might have a direct link to the loss, such that you have, for example, in the case of computing gradients, other ways to update the weights. Okay, so you don't have this big chain of products here. And that proved to be very helpful for gradient propagation. And that's from the theoretical side. From a more representation perspective, we can see these added skip connections as being a way to diversify the features at each step of the network, which proves to be very helpful. And in terms of error rates, this network achieves a much lower error rate than the previous one. So we went from 6.7 to 3.6 on ImageNet. And it was a good trick to use in summary. And then other people followed up on that idea of adding connections between blocks of layers. So for example, here it's an architecture called DenseNet that uses the same principle, except that it connects whole blocks of layers together, and it's achieved a small performance improvement. So this was a good solution to use because it proved to diversify the features at each block even more than before. Okay, so these are, okay, and today I think the best architectures also achieve around the same error as the ones I've mentioned. So this problem is kind of, we reached a point of stagnation of improvement. I think we are doing pretty good now. So I've talked about 2D architectures. Now, what if I had a 3D problem to solve? So people came up with different ways of dealing with 3D data. So one of them was to use 2D architectures and to use multiple views of an object, projecting them to 2D, and then doing the classification in 2D in order to deal with this 3D problem. So that's the first approach. And then you might say, these convolutions you use for 2D, they should be very similar for 3D. Then I would say, you're perfectly right. We could very well use those convolutions in 3D as well. The thing is, in 3D, the computations we do tend to be much less efficient than the ones in 2D. And I will illustrate that fact with a very simple example. So let's suppose that I am in 2D, okay, and that I'm interested in classifying images for which features are contained in a specific region, okay? For the sake of simplicity, let's suppose that that region is a circle, okay? So in 2D, your problem would amount to something like this. You have your image, and then you have your interesting features, contained in a circle. Okay? Let's suppose that that circle is of radius r. Now, this is the illustration of the problem you're trying to solve in 2D. But now let's suppose that you also want to solve this problem in 3D. Let's represent the equivalence representation of this situation in 3D. So in 3D, instead of just an image, we'll have a volume, okay? And instead of a circle, I'll have a whole sphere. Still of radius r. So that means that each dimension of the input, let's call it 2r, okay? Now, I'm saying that in 3D, computations, it seems that computations will be much less efficient because of a melody that you might have heard before, that the higher you go in dimensions, the farther points gets one from another. And we will see that with this very simple example. So here, for example, if I want to compute the ratio of the surface of the image with respect to the surface of the circle, this calculation will lead me to, okay, so surface of the image is 2r, so it's 2r squared, the surface, over the surface of the circle, pi r squared, okay, which is approximately, which is exactly 4 over pi. And since I like physics, I say pi equals 3, so it's approximately 1.25. Okay, so you have 1.25. So the ratio, of the total surface is exactly 1.25 times what's interesting for you. And in the case of 3D, if we compute the same ratio, we get, okay, with the same computations, a value that's much higher. That's of 2. So that means that, let's say you have something that's of interest for you in your convolutions. When you perform your convolutions in 3D, you will tend to perform convolutions on features that don't matter that much to you. So that's translating the fact that there is more emptiness in 3D than in 2D. And yet, these convolutions prove to be useful in certain situations, especially in biology or in medicine, where people use these kind of networks to detect tumors, and they prove to be quite useful for these purposes. And now I'm going to give it to Zara, who will talk to you a bit more about how the parameters in ConvNets are related to each other.
Hello. Thank you, Sherwin. Sherwin gave us a great review on how convolutional neural network evolved by today. I'm going to give you more details on how a convolutional neural network works. Suppose you have a picture, a cat picture, and you want to classify it as cat or not cat. Suppose that the dimension of this figure is 1,000 pixel by 1,000 pixel, and this is a RGB picture, meaning that it has 3 channels for red, blue, and green. So the total number of the features in this figure will be 1,000 times 1,000 times 3, which is 3 million. If you want to use a standard neural network to classify this figure, and suppose you have only 1,000 hidden layers, hidden units in the first layer. So the dimension of the parameters of your neural network only for the first layer will be 3 million times 1,000, which is 3 billion. So you need to store 3 billion parameters to only represent the first layer of the convolutional neural network. So you need a huge resource for the storing these parameters and also for computing using these parameters. The second limitation of this sort of having big images in computer vision is that basically if the number of the input features are 3 million, it means that if you don't want to have overfitting, the number of the training samples should be more than these 3 million. So you need to have more than 3 million training samples, which in many cases it is impossible. So to overcome this problem, people propose to use convolutional neural network. To start, let's look at a very simple example and a motivating one, how edge detection works. Consider this figure. As you see, this figure have the horizontal edges and vertical edges. And the goal we are looking for is detecting the vertical edges or the horizontal edges. How we should do that? Let's consider a very simple matrix. As you see, it's like 6 by 6 matrix, and then at the left-hand side, they are all 10, and the right-hand side, they are all 0. If you want to plot this image, this matrix, it looks like the left-hand side can be represented as bright picture, and the right-hand side can be represented as dark, like this one. In convolutional neural network, they introduce filter or kernel that they want to convolve this filter to the input picture. This filter is specifically a vertical edge detector, which if you plot looks like this. If you convolve this picture, this filter to the input picture, the result looks like this. Why we have this output? So basically how does it work is that you just first to start copy and paste the filter on the top left hand side of the input, and then do element-wise multiplication of the elements. So for example, here it will be 10 times 1 plus 10 times 0 plus 10 times minus 1 plus 10 times 1 and till end of the matrix. And the result will be 0 stored here. For the next pixel in the output, you just shift this image one more to the right, which will be here, and then do the exactly same process. And then the result will be saved in this pixel. So as you see here, the output results, if you plot the output result, it looks like this. So the middle part is bright, and then the left and right sides are black. So remember, this is a vertical edge detection. So the goal is finding this edge between the bright side and dark side. And at the end, what we have is like the middle part is bright, which is an indicator of them having a vertical edge on the middle of the image. What happens if you want to detect the horizontal edge? To detect the horizontal edge, what we need is only flipping this vertical filter to 90 degrees and having this horizontal filter. As you see here, we hard-coded all of the parameters of the vertical and horizontal filters. But what happens if you want to detect the edges at 45 degrees, 75 degrees, or 90 degrees, or any arbitrary pattern? Of course, we cannot hard-code all of them. So how a convolutional neural network works is that instead of hard-coding them, let's assign some parameters to them, W1, W2 to W9, and the model learns these parameters for us based on the data set that we feed through. Padding. padding is one of the building blocks of a convolutional neural network. So if you remember in the previous picture, I show you an input 6 by 6, which was convolved by a filter 3 by 3, and the output was 4 by 4. So as you see, the general formula for this sort of the convolution is if the input is n by n and the filter is f by f, then the output side will be n minus f plus 1 times n minus f plus 1. It means that the output size is smaller than the input size. So if you have multiple convolutional layers, your output at the end will be shrink. And you're not able to do the convolutional layers and have the convolutional layer as many as you want because your output will be shrink. So to overcome this problem, they introduced padding. Padding looks like if you add another pixel around your input pixel. So for example, here equal to the one unit of the padding, which means that you added two rows on the top and two rows on the top and 2 rows on the sides. If you do the padding, you are able to preserve the input size. Using the padding, the size of the output will be n plus 2p. P is the unit of the padding. For example, here p is 1. Minus f. F is the size of the filter. Here is 3. Plus 1 times the same thing. So another reason that people do the padding is that if you don't do the padding, consider the pixels on the edge of this input image, right? So the only time that you conclude these edges on your output is when this filter is convolved on them. So basically, for example, for this one, this picture, there is only one convolution that considers this pixel in the output, right? But for example, for the centers, there are more convolutions that consider this one in the output. So what happens if you have some important things in these edges, right? You want them more in your output. So based on what I described, there are 2 types of the convolution, valid and same convolution. Valid convolution is basically what we described at the first, means no padding, means the size of the output is smaller than the size of the input. But the same means that we pad so that the output size is the same as the input size. As I said, the output size is n plus 2p, p is the size of the padding, minus f plus 1. And the size of the input is n. So if you want the size of the input be same as the size of the output, the size of the padding will be f minus 1, f is the size of the filter, over 2. This might explain why in many cases people suggest use an odd number for the size of the filter, because you want to decrease by 1 and then divide by 2. Strided convolution. Strided is another building blocks of the convolutions. So basically, you remember in the previous slide that when we copy and paste the filter in the top corner, for the next step, we just shift this filter by 1 to the right. In that case, the stride is equal to 1. But if it's instead of 1, if we shift it to 2 units to the right, the size of the stride will be 2. So, okay. In that case, the output, the size of the output will be exactly same as the size of the output that I previously said, but over the S is the stride. So if you have the stride and padding at the same time, the size will be n plus 2p. P is the size of the padding, minus f, size of the filter, plus 1 over S, where the S is the size is the stride. I think you had the same problem for the midterm. Convolutional on RGB image. So far we've been talking about a grayscale image where we only have one channel. So what happens if we have RGB image with 3 channels? So basically in this case, you need to add more layers to your filter. The depth of the filter should be same as the depth of the image. So here, if you have 3 channels here, you should have 3 channels for your filter too. Basically everything is same. The size of the output is 4 by 4. But when you are doing the element-wise multiplication here, remember that you should do it for the whole cube, right? For the whole cube of this filter. Multiple filters. Oh, one thing I forgot to say is that here you have the option to ask each layers of the filter to do different job for you. For example, I asked the filter to detect the vertical lines or vertical edges on the red layer and do the horizontal edge detection on the green layer and do something else on the blue layer. So here you have the option to choose the weights for different layers such that they do different things in different layers. Another notation. So what happens if you want to detect vertical edges, right, as well as horizontal edges, as well as the other functionalities, as well as other function on your input image? It's obvious that you can't do it all by one filter. You should have multiple filters. So the question is how you should use the output of the multiple filters in this case. For example, here, this filter do a vertical edge detection and you store the results in this output. Another filter do a horizontal edge detection and you store the output in another matrix. So the final output will be a stack of these two and will look like a cube. That's why in the convolutional neural network, you see a lots of cubes. This one shows an example of the ConvNet. Suppose the input that you feed through your neural network, the size is 39 times 39 times 3. And then the size of your filter is 3 by 3. And then the stride is 1, padding is 0, and you have 10 filters, right? So you should have, so your output depth should be 10, which is the same as the filter that you apply. So this is your output. And then if you do this calculation that I mentioned here, n plus 2p minus f plus 1, this is the resulting output. If you do another filter, if you apply another filter and convolve another filter here, this will be the size of the output and so forth. So at the end, for example, for the example that I just introduced for finding if an image is a cat or non-cat, so as you see here, the size of the final output is much less than the size of the input that you apply, right? So here you can put them along through a vertical vector and feed into a logistic regression to find the confidence level of if this input is a cat or if it is not cat. One more thing is that you shouldn't, if you study math, probably you see convolution in the math too. So basically the convolution that we introduce is different from the convolution that you see in the math. It's mostly cross-correlation. Yeah, thank you.
Okay, thanks, Sherwin and Zara. So we just talked about the details of convolutional neural networks, and next we're going to talk about some applications. So as we just mentioned, like the task of classifying if a picture is cat or not is one of the image classification tasks. So given an input image, we're going to try to classify it into object classes. So there are multiple classes, and we could output a probability for each class, and we're going to choose one that has the maximum probability. So we have this ImageNet as a big visual recognition challenge dataset. So it contains 1,000 object classes and more than 1 million images. So every year we do this challenge, and we can see that the best model that achieves the optimal error rate every year. So as we can see on the rightmost column, the human error rate is around 5.1, and currently our deep learning model is achieving a better error rate than even the humans. So we can notice that in the year 2012, the error rate drops a lot. So that is a year that the convolutional neural networks come into this task and achieves a very good result. So this evolution of the convolutional network these years has become big. So from the year 2012, the supervision, which is also the AlexNet, that has 7 layers at that time. And then in the year 2014, there comes the GoogleNet. And then in the year 2015, the residual network at that time has 152 layers. So that means the convolutional network, the trend is that the network is getting deeper and deeper. So the model gets more complicated and works better and better each year. So this one is it's an image caption generation. So we can see an example here. So in this task, given an image, we're trying to generate a caption. So that means, for example, we can choose a random image. So just for example, for this image, so in this picture, there's a man in a black shirt is playing a guitar. So in this case, from this image, we're trying to generate this sentence that describes the image. So this is a task that we can combine the convolutional neural networks with other networks. So for example, in this case, in this case, given an input image, so we can first go through a convolutional neural networks that do the feature extraction. So in this use case, we use the CNN as a feature caption. So after some convolutional layers, we can capture the high-level features of the image. And then the next step, we go through an RNN with attention mechanics. So in this step, the attention works as a function that captures the context of what is output from the convolutional neural networks. And then from that step, we can go through an RNN with the word generation so that we can capture a feature with a bird, and then we generate the word that like a bird. So in this case, we can generate a sentence from the output of the feature from the image. And a next step is image color. Another example is image colorization. So the input will be a grayscale image, and then the CNN will automatically color it. So one ambiguity about this case is that from one grayscale image, there could be multiple ways to generate the colorized images, and all of these images could make sense to human eyes. So in this case, the CNN will still go through the convolutional neural layers, and then in the final layer, we're going to output the probability distribution for each pixel, so that we use an LAB, the lab colorization method. So the input, the grayscale images, will be the L layer, which is the lightness, and then we output the AB layer, which is the colored pixels. We can see a demo here. I'm not sure we'll be able to open this, but So the grayscale image input, and then we'll be able to see how the colorization work on this photo. And another way to resolve to solve the ambiguity that there could be multiple ways to colorize this image is that we can input some. We can give the algorithm some user input. For example, in this image, we can select a pixel, and for example, on the shirt, we select this pixel and specify it to be, for example, purple or blue or yellow, so that our algorithm will take in this user input and minimize the total loss. So a next example is the image style transfer. So in this application, given two images, so one on the top and then one on the bottom, the first image will give us the content of the final output, and then the second image will give us the style of the output. So we use the style of the second image to transfer the first image. In this case, we have the two images will go through the convolutional network separately. So for example, the first image on the left, this is we'll talk about the style image on the left, this case. So as it go through the convolutional networks, there's also another image in the middle, which is a random noise image. So after it goes through the convolutional neural network, we will compare the difference between this style image with the random image. So we have a sum of difference between each pixel, between these two images. And then this will be the style loss. And similarly, on the right side, we have the content image. So we also compare this with the random noise image. And then there will be the content loss. And the overall loss will be a linear combination between the content loss and the style loss. We're going to try to minimize this objective function. And then we have another application. Instead of just talking about images, we can also apply it to videos, which is similar to images, but we also need to capture the temporal information. There are some large video classification data sets, for example, the UCF 101 and Sports 1M or YouTube 8Ms. So these videos will give you a short video clip, and then they label what actions or just what is happening in this video. And then from the CNN, we want to capture the temporal information. So there are multiple ways to do this. From the CNN, we are doing a single frame convolutional network. And then since we have multiple image frames stacked together, so one way to combine them together is using the late fusion. So that means each video frame will go through a separate convolutional neural network. And then in the final layer, the fully connected layer, we're going to combine this information together so that this late fusion, the last layer, will have access to the information from these image frames. And then there's another different method using the early fusion, which is combining the image frames at a pixel level, so that before going to the convolutional network, we combine the pixels in the beginning and then go through one convolutional network. And another method is using the slow fusion, which is a mixed method between the late fusion and the early fusion. So we combine them in the middle, and in the end, the result will also have access to all these images at the pixel level. So these are the methods to do the video classification, which is also based on the image classification base case. So yeah, here this is some example usages of the convolutional network, and there are more applications online. You could explore that. Yeah. So that's all for today's section.